So the semi-classical approximation that we're considering is where the state factorizes into a coherent state for each single particle mode. And it's also called the mean field approximation because the expectation value, or the average, of the field operator is just equal to the complex number that parameterizes our coherent state. This complex number comes up in other kinds of semi-classical approximation as well. It's often called the order parameter because that one function or that one complex number defines the entire quantum state. So in some sense, this approximation has imposed a lot of order into that state. Now we can get expectation values of arbitrary strings of creation and annihilation operators, provided they're in normal order such that all the creation operators are on the left and all the annihilation operators are on the right, because then the annihilation operators simply act to the right to give us coherent state eigenvalues, and our creation operators act to the left to give us the complex conjugates of our eigenvalues. Now supposing we're making this approximation, how are we going to figure out the dynamics? How are we going to find out how our order parameter or our mean field evolves over time? The easy way to do that is from the Heisenberg equation of motion for the field operators themselves. And then from that line, you simply take the expectation value of both sides. And then it's a simple step to turn those expectation values into the coherent state complex numbers. And that is called the Grotowski equation, or sometimes the nonlinear Schrödinger equation. And it's fairly obvious why it's called the nonlinear Schrödinger equation. If we look at this part here, it looks exactly like the Schrödinger equation for a single particle in a potential v of x. And this extra term here is just a nonlinear term. It looks like it's got a potential that depends on the wave function itself. And so the atoms are either attracting each other or repelling each other. People look at that and they often get confused. They think, hey, that's the Schrödinger equation. That looks pretty quantum, so why is this called semi-classical? And the answer is, of course, it's fully quantum for a single particle. And indeed, you can't have that nonlinear term for a single particle. But it looks like a Schrödinger equation for a single particle. But we're talking about the dynamics of a collection of particles, a very large collection of particles potentially. And so we're actually ignoring a lot of the quantum features and a lot of the potential structure. This is often called a macroscopic wave function. So people might describe, for example, a Bose-Einstein condensate as all the particles being in one big macroscopic wave function. Exactly the same approximation is often made in quantum optics, where we replace a large coherent mode with just a field, and that's of course our electric field. So our classical notion of an electric field or a magnetic field comes out of a semi-classical approximation to the quantum field theory. So if we discovered photons first and done a quantum field theory for them and then made a semi-classical approximation, we would have discovered classical electromagnetic theory. And here we have an equivalent classical field theory for particles, scalar particles. We do have to remember that these semi-classical approximations are indeed just approximations. And indeed, while assuming that everything's in a coherent state was a very fast way of getting to the nonlinear Schrödinger equation, we can see that there are some problems with it. We get that particular Heisenberg equation of motion, this one here, from a Hamiltonian that has a normal kinetic energy term, a potential term, and an interaction term. And if we look at that interaction term, and if we look at the actual evolution of the real states, even if we start in a coherent state approximation, a semi-classical approximation like we've shown here, then in fact that coherent state does not stay as a coherent state. So although we've created this nonlinear Schrödinger equation, and we've said, if it were a coherent state, this is how it would evolve, it doesn't actually evolve like that if it's a coherent state. Now, surprisingly, the differences turn out not to matter very much. And to explain that, there are variants of the derivation that we showed here that are a bit more complicated, and they make just subtly different approximations to the state of the field. And the total field is still characterized by some complex valued function, phi of x. And the evolution equation we get for that order parameter turns out to be this same Grotowski equation, this same nonlinear Schrödinger equation once again. Why is that? Well, in the limit that the interactions are zero, it basically has to look like a bunch of independent particles. And independent particles are going to act just like the single particles. And so that order parameter has to evolve like the Schrödinger equation. And the nonlinear term, where the particles are attracting or repelling each other, dimensionally has to look very much like that. And it turns out that almost no matter what semi-classical approximation you make, you end up with a term in your order parameter evolution equation that looks exactly like that up to some very minor corrections in the prefactor. And so the nonlinear Schrödinger equation comes up again and again no matter what semi-classical approximation we make. And what we've done here is we've shown you a very efficient way of deriving it using the coherent state approximation.